hear me well now? Right. Please respond if you can hear me in the chat. Oh, perfect. Thank you. Right, lovely. Now, today, just to be clear, I was collecting some feedback, and some people said that the questions in the webinar are not like in the assignment. Well, actually, they are. They're very much like in the assignment. I don't always point that out. So today, the first time ever, we're actually going to go through one of the problems. I won't do it to the end. I'll just give you a head start, but I'll go through probably 75% of the problem. I'll go through the toughest part, because one thing I realized, the first time I did it wrong, and the second time over, I understood that it's a much harder problem than I've anticipated. But that means we'll have some stuff to do. Anyways, and so we're talking about energy. Then there were some a few key principles involved. Well, the work energy principle. Yeah, so the work that you do goes into changing the kinetic energy of an object. That's a very important thing. You probably understand it intuitively, but you should be able to always write the following expression, that the work is equal to the change in kinetic energy. And that's super important. We'll be using this in every single problem. The first one is a classic question, classic problem. This is to do with conservation of momentum and conservation of energy. When a bullet is shot from a rifle, the momentum of the bullet is the same as the momentum of the gun. Okay, how come the bullet has so much more destructive power than the recoiling rifle? Okay, so and there's just a few things I want to point out here. This is to do with explosions. It's more related to momentum. So we have a gun and we have a bullet. The bullet is leaving the gun. The gun is mass m. The bullet is mass m. The bullet is traveling at velocity v. The gun is recoiling at velocity u. And of course, mu is equal to mv. So u over v is equal to m over m capital. Or in other words, the speed of the bullet divided by the speed of the rifle is equal to the mass of the rifle divided by mass of the bullet. So if the rifle is 10 times heavier than the bullet, that means it travels 10 times slower. That's from the conservation of momentum. And I'm doing modulus here. I don't care about the signs at this point. But the key thing that when we start to calculate kinetic energies, kinetic energy 1 is equal to 1/2 mu squared, and kinetic energy of the bullet 2 1/2 mu squared, and you find the ratio kinetic energy of the bullet divided by kinetic energy of the rifle, you get an interesting thing. So because you have kinetic energy of the bullet is 1/2 mu squared divided by 1/2. Sorry, that's mv squared, of course. mv squared and mu squared. So 1/2 cancels out. V squared over u squared. That's m capital squared over m small squared, which incidentally is m over m small. And the significance of this result is that if the bullet is 10 times lighter than the rifle, it will have 10 times the kinetic energy. Okay. So this is just one thing I wanted to mention. It's a very quick problem. But it is important to consider because we will be talking about the kinetic energy paradox. This plays a role in there. So the kinetic energy of the recoiling rifle is much smaller than the kinetic energy, and that's why the destructive power of the bullet is much bigger. Okay, I hope that makes sense. It's not a difficult result, but it's just something I wanted to point out before we properly start. So I could have called it problem 0 and get on with it. Right. So a boy, mass 50 kilograms, is standing on a stationary skateboard on a smooth surface. He throws a ball of mass 10 grams at the speed of 10 meters per second relative to the ground. Find the change in the kinetic energy of the ball. Okay, so that's simple. Change of kinetic energy is equal to 1/2 mass 0.01 times 10 squared. Well, we know the ball started stationary, and the boy throws the ball, and now the ball has kinetic energy. So the change in kinetic energy is the initial kinetic energy minus the final kinetic energy minus the initial kinetic energy, which is the final kinetic energy, which is 2 joules. Yeah. Is it 10 grams, 100 times, yeah, 2 joules. So, and by the work energy principle, the work done by the boy is equal to the change in kinetic energy of the ball, which is 2 joules. Okay, with me so far? Now the boy is actually traveling at 10 meters per second. Might be, yeah, 0.5 joules, sorry. 0.5 joules. 0.5 joules. The work done by the boy and the change of kinetic energy of the ball is 0.5 joules. Nice. Now, then we look at the second case. Now consider the boy is traveling at 10 meters per second. So the boy is traveling now. And he's already traveling at 10 meters per second. And he's throwing a ball. He's throwing a ball with the same, and he's using the same energy, the same force to throw the ball. And of course, the ball is now traveling at 20 because 10 plus 20, 10 plus 10 is 20. So the change in kinetic energy of the ball is the final kinetic energy is 1/2 times 0.01 times 20 squared minus the initial, which is 0.01 times 10 squared, which is slightly bigger. So 20 minus, so it's 400 minus 100. So it's 300. 3 over 2 is 1.5 joules. 1.5 joules. So what's going on? I mean, the boy didn't throw harder, because if the boy would threw the ball harder, it will fly faster than 20. He used the same force because he is in an inertial reference frame, right? The laws of physics are not different if you're moving. So how come it had more kinetic energy? Well, the thing is that which we did not take into account is that when the boy throws the boy starts to move as well. And really, considering the previous example, the boy is so much heavier than the... So if the kinetic energy of the ball is 0.5 joules, and the ball is what? The ball... So if the kinetic energy of the ball is so change in the kinetic energy of the ball is 0.5 joules. 5 joules. So when stationary. And we have seen that we need to calculate the ratio, the change of the kinetic energy of the boy is mass of the ball, so 0.01, divided by mass of the boy, which is 50 kilograms, times 0.5. So 0.5 times 0.01 divided by 50. That's 10 to the minus 4 times 0.5, which is 10 to the minus 4 joules. That's a negligible amount. Like, we really don't consider that. But let's calculate the change in the velocity of the boy. Change the velocity of the boy, and we will see that we will change in the velocity of the boy. We need, so the kinetic energy is 1/2 mv squared. So mv squared, so 2 times the energy, 2 times 10 to the minus 4. Well, it's 2 times kinetic energy of the boy divided by mass of the boy, and square rooted. So 2 times that divided by 50, and square root of that, 2. So that's 0.002 meters per second. Like, I mean, this is a tiny amount. It's a tiny energy and a tiny change of speed. But then when moving, so the boy starts off traveling at 10 meters per second, and the kinetic energy is 1/2 times 50 times 1/2 times 50 times 10 squared. So the kinetic energy of the boy is 0.5 times 50 times 10 to the power times 100, 2,500. 2,500 joules. But then when the boy is moving at 9.998 meters per second, because after throwing the ball, the speed has changed by this amount, by this number. The kinetic energy is going to be, surprise, surprise, 0.5 times 50 times 9.998 squared, 2,499 joules. So that's where the extra joule came from. So energy is conserved. The boy did not do more work. Well, I mean, the boy kind of did more work because because his body is already moving, and when he's throwing it, kind of the moving body does some work. Do you understand this on a scale of 0 to 10? Do you understand what's going on? Do you understand what the surprising bit was and how it has been resolved? Okay. So basically, we have, this is called the kinetic energy paradox. When you are in a moving frame of reference, somehow it seems like energy is not conserved, but it is. Because the boy did the same amount of work, but caused a different change in kinetic energy. And this is due to the boy's movement. And because his change in energy is very insignificant when he's stationary, but when he's moving, this change which change is more significant. The change is by 1 joule, which is enough to give the extra joule of energy to the ball. Okay. Problem 3. Now, problem 3 is scaringly close to one of the problems in the. It is about a car. It is a difficult question in the way it's phrased. This is an easier version. A car of mass 1,000 kilograms is stationary. The engine delivers full power of 1,000 brake horsepower. Brake horsepower is about approximately 740 watts. The friction coefficient is 0.8. Find the initial acceleration of the car if the car is 2-wheel drive and the car is 4-wheel drive. So how should that make any difference? Well, actually, you know what? We'll do 4-wheel drive first. 4-wheel drive and 2-wheel drive. So can somebody help me with this? Maybe you can use your mic and tell me what's going on. How do you even approach a problem like this? What's going to happen? There's more friction. By more friction, you mean more grip. True. Yeah, absolutely. But how do we calculate that? What formulas do we use? If you remember the question about the hula hoop, this is somewhat similar to the hula hoop question. Anyone? Come on, help me. Let's make it an interactive session, a more interactive session. Well, let's look at the problems. So we write down the work energy principle. The work energy principle is that the change in kinetic energy is equal to the work done. And the work done is obviously power multiplied by time. Change in kinetic energy. So because it's starting from standstill, change in kinetic energy is 1/2 mv squared, which is equal to PT. So V is going to be equal to 2 PT divided by m square rooted. And it doesn't seem like a big deal, but to find acceleration, we need to differentiate that. Acceleration is the derivative of speed, dv dt, and dv dt, so that's square root of 2 power time divided by m. These are constants multiplied by 1/2 square root of t. Okay, I have to write this down. I have to write this as square root of 2p over m multiplied by t to the power 1/2. Yeah, does everyone understand how I differentiated it? So I differentiate that this is a constant, and the derivative of this is 1/2 t to the power minus 1/2, which can be simplified as 2p divided by, well, 4t, which is square root of p over 2t. So how can we find acceleration from here? The initial acceleration. Initial means what? What does initial means? Which value are we getting? T equals 0. So when t is equal to 0, acceleration is what's the acceleration if t is 0? Come on, you know it. You don't be afraid. Guess. Why is it 0? We are, George. We are. So what's the problem with that? We get an infinitely big value, or undefined, or in physics it usually means infinitely large. So not possible. So what's going on here? Like, let's try to draw a graph. Let's try to draw a graph. So if this is V versus T, well, we all know the shape of this graph. It's a square root, so it looks like this. The graph looks like this because that's the relationship between V and T. And obviously you can see that the gradient of that graph, which is acceleration, is infinitely large in the beginning. So the car starts with infinite acceleration, but that's not possible. According to this, so the problem is, starts with infinite acceleration, which is not possible. It is not possible. The problem here is that we assumed that all the power is delivered to increasing the kinetic energy of the car. But actually, no. Some of this energy will go into thermal. Why is that? Well, if you try to deliver 1,000 brake horsepower to the wheels of a car, the wheels will start spinning. You've probably seen drag races. The wheels start spinning, and that's where the extra energy is going. So some of the energy is going into accelerating the car, but some of the energy is going into thermal energy because you are spinning the wheels. Does that make sense? If you're confused, tell me. You start by spinning the wheels. But if the wheels are spinning, the only force driving the car forward is the friction force. And the problem becomes incredibly easy. If the four wheels are driving, you have the friction force, mu times r is the friction force equals mass times acceleration. And mu r is mu mg. So the only force driving the car forward is the friction force. And the friction force is equal to mu r. Okay, it would be mu r1 plus mu r2, of course. Mu r1 plus mu r2, so it's mu mg equals ma. So acceleration is equal to mu times g. And that's the answer. Acceleration of the car is mu g. All right. We needed this to prove that the wheels will spin at the beginning. But finding the acceleration is incredibly easy. It is constant up to a certain point. Because as you can see, the relationship is not is linear. It's proportional to the square root of t. So if acceleration was constant, it would go like this. But at some point, when the wheels stop slipping, it will follow this curve, which is important. And this is something you will need to do in your problem, in your assignment. Well, actually, you will need to find the relationship. So the acceleration is mu g, so 0.8. Well, for simplicity, we'll assume g is 10, so it's 8 meters per second squared. 8 meters per second squared. And for a two-wheel drive car, well, the acceleration ma for a two-wheel drive car, so that's for a four-wheel drive. For a two-wheel drive car, it's going to be ma equals mu, let's say if it's back wheels driving, mu r1. And we can safely assume that half of the reaction force is delivered by the back wheels, although in true racing cars, it's more than that. It's about like 60-70% of the mass of the car is pushing on the back wheels. Anyways, ma equals mu r1, which is safe to say 1/2 mu mg. Therefore, acceleration is equal to half of that, half mu g. So it's 4 meters per second squared. Very simple. I mean, it is a somewhat sneaky problem, but there's loads of stuff to think about. You can't accelerate infinitely fast. So if you try to deliver that much power to the wheels, it just won't accelerate as the way you want. All cars are limited. The acceleration of every single car in the world is limited by the friction coefficient times gravity. And the friction coefficient is very rarely more than 1. So usually the cars don't accelerate faster than g, except when they're falling. Right. Okay, problem 4. Problem 4 is actually the problem from the assignment. I'm going to leave it to the end because I can spend an hour doing this. Just very quickly doing this. Problem 5. A hairdryer pushes cold air, which leaves at 20 meters per second. So you have a hairdryer. And which pushes cold air. So cold air at 20 meters per second. 20 meters per second. So we attach it to a Newton meter. So basically we set up a Newton meter here, and we measure the force which pushes it back, and the force is 2 newtons. That means that it pushes the air with a force of 2 newtons as well. It pushes with a force of 2 newtons, and the air travels at 20 meters per second. So you need to find the power. Well, we know that power is equal to, well, we know power is equal to force times speed. But that's not really the case here because the fan is not moving. It's the air that is moving. So it's not this, unfortunately. What happens here? We need to find, so the work is the change in kinetic energy. Change of kinetic energy of the air. So the work is power multiplied by time, of course. And the change in kinetic energy is 1/2 m, the mass of the air. So that's the mass of the air times the speed of the air, which is u, u squared. Now, what to do with the force? Well, the force, so on the other hand, that force is equal to change in momentum divided by change in time, or divided by time. I've used t here, change momentum. So it's the air starts stationary and changes velocity up to 20. So the air has changed this by mu divided by t. So mu can be written as ft, which is the mass of the air times the speed of the air, force, and time. And we can, well, there are different ways we can do this. I would do just like this. Pt is equal to 1/2 mu times u. Yeah, the mu squared is mu times u. So I take the mu and just plug it in here. So that's equal to 1/2 f u. That's very nice. It's a very, very easy solution. So, oh, sorry, f u t, of course, f t u. T cancels out, and the power is 1/2 fu. Yes, thank you. Well, power is 1/2 fu. So it's not fu, it's actually half of that. So what's going on? Well, actually, what's going on is that this formula only works for constant velocity. But here the velocity goes from 0 to u. So the average velocity is 1/2 u. Yeah, if it accelerates uniformly from 0 to u, the average velocity is 1/2 u. And that's why it's 1/2 fu. And of course, it's 1/2 times 2 times 20, which is 20 watts. Typically, a hairdryer is to 2000 watts. Well, because it spends most of its energy heating up the air. And it's a different story. Then if you want to find the power, you do power times time. Power of the heater is mc delta temperature, and so on and so on. But actually the fan doesn't take that much energy. So this is quite a realistic value. Okay, problem 6. A jet ski is traveling at speed v. The water is ejected at speed u relative to the jet ski. Find the efficiency of the engine. And this sounds very far-fetched in a way. So how do we do it? Well, we'll start with a picture. We'll start with the picture. And so this is some kind of boat, a jet ski. So what a jet ski does, it sucks in the water from the bottom or from the front. So the water comes in and it is thrown from the back at a high speed. This is how jet skis work. And conservation of momentum, of course, and this pushes the water back, pushes itself forward, so it propels itself forward. Now, because it's traveling at a constant speed, that means that the force provided by the engine is equal to the water resistance force. So water resistance is equal to the force from the engine. Force from the engine. The impulse delivered by the engine is F delta T. So F delta T. And if the engine has useful power, this would, because the useful power is actually the force multiplied by V. So this would be the impulse is FT, F delta T, which is useful power divided by V, by the speed of the boat, times delta T. Because to find the efficiency, the efficiency is the power useful divided by the power total. So the useful power is actually the power that propels the ship forward, but also throws a lot of water from the back, which has lots of kinetic energy, which isn't that's not very useful. And that's what we mean by efficiency. Efficiency is how much of the kinetic energy of the kinetic energy is actually wasted. Okay. All right. Now the total power. So the total power is, you need to understand that the total power can be calculated in the frame of reference of the ship. So you are in the frame of reference of the ship. What you see is you see water coming towards you at a speed v, sorry. Water coming towards you at a speed v. And water leaving you, the ship, with a speed u. Okay. Sorry, there's a lot of background noise. I think I need to clarify. We are talking about two different frames of reference. First, the frame of reference where the water is stationary. So initially, the water is stationary. So this is frame of reference where the water is stationary. Frame of reference of the stationary water. Frame of reference of the stationary water. The water initially is stationary, u equals 0, but let's some initial, V initial is 0. And it is being thrown out of the back of the jet ski. But the jet ski is traveling at speed V and throwing the water back at a speed U. So the speed of the water is going to be U minus V. Because V is the, U is the speed relative to the boat. Right? The water is ejected at speed U relative to the jet ski. Does that make sense? Why it's U minus V? So the change in momentum of the water, is equal to M U minus V. And now we go back. So impulse is this. And we know that the impulse delivered to the ship and to the water has to be the same. So impulse is that. So M U minus V has to be equal to power useful divided by V times delta T. And from here, I can find P useful equals M V U minus V. Do I want delta T in there? I don't really want, but okay, just for the sake of it, delta T. That's the useful power. Now we need the total power. And now we go into the frame of reference of the ship. In the frame of reference of the ship, the water reaches you with initial speed V. So V initial is V. And V final is U plus, no, U, sorry, not U, just U. So the useful power, the total power input, the total is the change in kinetic energy of the water over delta T, which the change of kinetic energy of the water is 1/2 mu squared minus 1/2 mv squared divided by delta T. And I hope you see where I'm going with this. This is going to be 1/2 m u squared minus v squared divided by delta T. And you plug that in. So you put that into here. And we get useful, which is mvu minus v divided by delta T over 1/2 m u squared minus v squared divided by delta T. Delta T cancels out. Mass of the water cancels out. We get v u minus v. There is the 1/2, so 1/2 2 goes on top, so that's a 2. And we have u squared minus v squared, so that's u minus v, u plus v, and 2v divided by u plus v. That's the That's the efficiency. Okay, that's the efficiency of the engine. And interestingly, when U is V, this efficiency becomes 1. I wonder what that means. This is something for you to think about. If U is V, efficiency C is 1. Very interesting. Okay, so we've done this one. Here, the purpose why I wanted to do this question is to show you, well, it's actually similar to the helicopter question. It's much harder than the helicopter question from the assignment, but it's there are a lot of things that you can pick up from here. So what I've been using Impulse. I've been using Impulse, and I've linked it to power a lot. And that's not the first time I've done it. I've done it before. And there are some important implications here to think about. Well, the efficiency of a jet ski. The useful energy is actually the energy spent pushing against the water resistance. The energy spent pushing against the water resistance is the useful energy. And the non-useful energy is the water being thrown at the back. Okay. And finally, to this question. Now, as I said, this question turned out to be way harder than initially thought, but I will go through about 3/4 of this question, and I'll leave you to finish it. That's my idea. So a heavy rope of length L is folded in half and held at both ends at single point above ground. One of the ends is released and it starts moving down. Find the acceleration of the free end of the rope when it has fallen a vertical distance of L over 3. Assume that there's no swing and no energy dissipation. So there's no friction in the rope. There's no friction here. The rope doesn't start swinging. So all of the energy goes into the kinetic energy of this bit. Now, on the other hand, it seems like the rope is in free fall. But and in free fall, it would have acceleration g. But I will show you that it's actually not. It's actually more than g. The acceleration of this end is more than g. Acceleration, which is more than g. And this is true about bungee jumpers. So when bungee jumpers jump off a bridge, they accelerate down faster than g, because some of the gravitational potential energy of the rope goes into their body. Okay, so in this case, the center of mass of the rope moves downwards, and all of that, and the change of the whole of the rope, the change of the gravitational potential of all of the rope goes into the kinetic energy of just this bit of the rope. So we have a flow of kinetic energy to gravitational potential energy. Change in kinetic energy equals to change in gravitational potential energy. Okay, so, and it is a heavy rope. Now, it's going to become very mathsy. So assume that this end has moved a distance of x. has moved a distance of x. That means that this length of the rope is L plus x over 2. And this end of the rope is L minus x over 2. Acceleration. Now we need to find the center of mass. Now let's assume that the center of mass, so I'm going to draw these two pieces of rope separately. I'm going to draw the first piece of rope and the second piece of rope. Piece of rope. And initially, they were like this. Initially, the ropes were like this. They were equal, or they were of equal length, and they were side by side. And let's say that this is where the center of mass was initially. This is the initial position of the center of mass of the rope. And this is the ceiling, of course. So this is the ceiling. So you can see that the, should bring them closer, because these ends are of course connected, but we don't care about this bit. Yeah. The center of mass was here. Obviously, the center of mass of this rope is going to be lower, and the center of mass of this rope is going to be even lower. Is everything making sense so far on a scale of 0 to 10? Please reply. Okay, thank you. So initially, this distance was L over 4. So in this bit, we're just doing geometry. So there's not much physics going on here. And this is 0. So we need to find this distance. Well, we know that the center of mass of this rope, because this rope is L. So let's call this x1, and we will call this x2. And this is x, of course. X. There are different ways you can do it, but I know that x1 is the center of this rope, and the center of this rope is L plus x over 4 minus L over 4. So x1 is going to be L plus x over 2 minus the initial position of the center of mass, which is L over 4, which is actually oh, sorry, L over 4, of course. L plus x over 4, because it's half of that. It's half of that, which gives us x over 4. So this is x over 4. So if this end moves x down, this end only moves x over 4 down. And x2, now x2, it's going to be x plus L minus x over 4, this bit, plus minus L over 4. L over 4. It's a bit complicated, but you can you can prove it for yourself. The center of mass of this rope is going to be 3x over 4. I won't bore you with details of how I got there, but you can prove it for yourself. Now we need to find the x. Sorry, the mass. This is M1, and the second rope is M2. So M1 is going to be. So we are interested in how much the center of mass actually moved, because that's the way we can find the kinetic energy. So M1 is the length of the rope divided by the original length of the rope, is L1 divided by L times the mass of the rope. And L1 is L plus X over 2. L plus X, L plus X over 2L M. That's the mass of the first bit of the rope. The mass of the second bit of the rope, very similarly, mass is L minus X over 2L times mass. Okay, everything clear so far? Can I get a quick vote, please? Okay, very nice. And then we just do the center of mass. So X center of mass is X1 M1 plus X2 M2 divided by mass, which is going to be slightly tedious. So X1 is X over 4. M1 is L plus X over 2L M plus 3x over 4. 3x over 4. L minus X over 2L M divided by M. So M cancels conveniently, and we have the movement of the center of mass. So it's going to be, well, X over 8L. X over 8L can be taken out of the bracket. And L plus X, so it can be L plus X plus 3L minus 3X. So we get 4L, so X over 8L, 4L minus 2X. I'm just wondering whether I want to expand this or not. I do. By all means, I'm going to expand this. So this is going to be X over 2 minus X squared over 4L. Wow. So we see that the center of mass, if this end moves down by X, the center of mass shifts by this value. And this might be just the hardest part of this question. It's just very mathsy. something that's not it's not very comfortable. But then you get this. You get an answer which makes sense. And then we go back to this expression. So the change of the kinetic energy is equal to the change in gravitational potential energy. We just need to figure out which gravitational potential energy we're talking about and which kinetic energy we're talking about. Well, the only thing that is moving is this bit, is this piece of rope. And this piece of rope is moving down with a speed v. So it's the kinetic energy of this part of the rope. So we need 1/2 mass m2 times the velocity squared. And this is equal to the change of gravitational potential energy of the center of mass. Because it's the center of mass that has lost gravitational potential. So we need mg and then this expression, x over 2 minus x squared over 4l. We know that m2, so it's 1/2. m2 is here. So it's l minus x over 2l m v squared equals mg x over 2 minus x squared over 4l. Now, m cancels. We multiply everything by 4l. So we go here. And, well, 2 and 2, that's 4l. So that's going to be l minus x v squared. Here, it's going to be 4l. Sorry, 4lg x over 2. Okay, I'll open. Okay, I won't skip steps. It's 4l g x over 2 minus x squared over 4l. Opening the brackets, it's going to be 2lgx minus l, so gx minus gx squared. Quick vote, are you still following? Do you still understand what's going on? Another vote. Okay. So, I mean, what we did is we have, so this is physics, but the rest is maths. This is physics, but the rest is maths. So just plugging in the values. But then after this journey, we come by a reasonably easy expression. xv squared equals 2 times L times G times X minus GX squared. Now from here comes the most interesting part of this question, is actually figuring out acceleration from this. Figuring out the acceleration from this. So what I'm going to do is I'm going to remember that velocity, and we're talking about the velocity of the tip, is dx dt. And acceleration is equal to dv dt. So what I'm going to do is I'm going to differentiate the whole thing. Yeah. I'm going to differentiate the whole thing. And it's going to be in terms of t, of course, because yes, differentiate in terms of t. I know L is constant, so this is just 2v, so it's going to be L. We keep the constant out. We'll keep it out. So it's going to be 2v, but then we have to use the chain rule. So dv dt, the chain rule, dv dt is going to be dv dv squared dt is going to be dv squared dv times dv dt. So this is going to be 2v dv dt. 2v dv dt, which is dv dt minus. Yeah, does everybody understand? So we got 2, so it's 2v times the derivative of dv dt, because I'm differentiating with respect to t. Is anyone confused? This is the chain rule. This is the proof. 2v dv dt. I'm not a fan of red in this case, but now here I have to use the product rule, because so it's going to be minus bracket. I'm just use brackets just for convenience. It's going to be dx dt. Okay, I'm a bit lazy here. Instead of dv dt, I'm going to write v prime. So here it's going to be x prime multiplied by v squared. That's prime plus x v squared prime. So v squared prime is going to be 2v v prime, the derivative, equals 2lg, that's a constant. So it's 2lg x prime. X prime with respect to t, of course, with respect to t, with respect to t, with respect to t, and minus gx squared. In a same way, is going to be g multiplied by 2x x prime with respect to t. And from here, well, this is acceleration. So it's going to be 2lva, where a, this is acceleration. This is velocity. This is acceleration. This is velocity. And this is velocity. 2lva minus v cubed minus xva minus 2xva equals 2lgv minus 2xgv. V cancels. Okay, and this becomes 2. So let's take a to one side because we're looking for a. 2l a minus v squared minus 2xa equals 2lg. Okay, not exactly what I wanted, but 2xg. So x is to one side. So x to x. No, sorry, we're a. We need a to one side. So a to a l minus x equals v squared minus 2lg minus 2xg, so 2g l minus x. From here, I find acceleration. Acceleration is v squared over 2 l minus x minus minus g. Why minus? This is plus. This is plus plus g. Ooh, that's an interesting result. So from here, you can see that acceleration is actually greater than g. Yes, bungee jumpers accelerate faster than g. Now, this is not the answer. Not answer, because you do not know v. Not answer. However, we can see that acceleration is greater than g. That's a very important result. And what you need to find v and plug it into here. And that will give you the acceleration. And then you substitute the distances. So I'm not going to go any further with this question. But this is, okay, I think I've done 95% of the problem. Not actually 75, but actually 95. But what's important here is that I've got an expression in terms of speed x, and then I differentiated it to get acceleration. In many problems, you can do that. You're allowed to do that. Okay. Any questions? Any questions on how to do that? The next step would be to actually attach the bungee jumper and modeling a bungee jumper. It's a lot of fun. It's a bit harder than that. There's actually a web page dedicated to physics of bungee jumping, and it's quite interesting. So you can model. And one of my students actually did some research on that topic. So he dropped a heavy chain and measured the acceleration of the tip. Quite fascinating results. And you do actually confirm that the acceleration is greater than g. So, I just googled physics of bungee jumping, and it popped up very similar equations to that. You can use conservation of energy to find acceleration, because the energy links displacement and speed. Yes, because mgh, h is the displacement, and v is the velocity. So if you carefully differentiate velocity, you get acceleration. And this is a powerful tool to solve problems in physics. I'd say, well, it's kind of closer to further maths rather than the A-level physics course. The A-level physics course doesn't do stuff like that, and it's a pity. Right. Okay. I hope you enjoyed today. I hope that was useful. And right. So. Oh yes. Next week there's not going to be a webinar. I'm finally getting some rest, and I'll see you in 2 weeks' time. All right. Enjoy half term. And
I just wanted to ask a quick question.
Yeah.
Can you quickly go over that conundrum of principle of conservation of energy, where you had more kinetic energy than you should have done?
Okay. So this is this is described in the assignment as well. There's a whole section dedicated to the to the kinetic energy. Look, let's say we have a car that goes from standstill to 10 meters per second. So it goes from 0 to 10. The change in kinetic energy, and let's say for a car of 1,000 kilograms, this is going to be half times 1,000 times 100. Yeah, times 100. So that's what, 200,000 joules. Now, from the point of view, so the change of the kinetic energy of the car is that. Now, let's say you were sitting in another car. You were sitting in another car, and you were traveling with a speed 10 meters per second. From your point of view, this car doesn't go from 0 to 10. This car goes from 10 to 20, right?
Yeah, I see. Yeah,
Goes from 10 to 20, and the change in kinetic energy is actually 1/2 times 100 times 1,000 times 20 squared minus 10 squared, which is actually 600,000 joules. So from the point of view of a person standing on the ground, the car has changed kinetic energy by 200,000 joules. But from the point of view of the person sitting in the other car, the car has changed by 600,000 joules. Okay. Now the thing is that here, when you are sitting in the car, the ground is moving. The planet Earth on which the car is sitting, it's moving. And when the planet Earth is moving, the car causes the planet to slow down. It's a very insignificant change for the planet, but that does account to the difference in kinetic energy. And
Wait, say
in
that
the
again. So, like, how does it make the planet slow down?
well, if you're accelerating, that means you're pushing against the ground.
Yeah. Oh.
So you're pushing the Earth backwards. To walk forwards, you have to push the planet backwards. And this seemingly insignificant change in kinetic energy of the planet actually is responsible for that difference, for the 400,000 joules. Because for the planet, 400,000 joules is nothing. Okay. So from the point of view of the person in that car, the Earth would lose 400,000 joules of energy, the planet, and this accounts for the extra kinetic energy.
All right. Yeah, I see.
There's a more detailed description in the assignment, so do have a look. And if you're still confused, do ask me in 2 weeks' time.
Thank you.
Okay, welcome. See you.